I wanted to quickly revisit something from last class. So last class we did this optimization bias, also known as overfitting on the validation set thing. And we did this experiment and we saw the cross-validation score was way higher than the test score, and that kind of worried us. So I just added this plot to the notebook from last class, where I keep one of the hyperparameters fixed, C, and I sweep the other hyperparameter. Oh, look at me not putting on axis labels. That's bad. This is the max df hyperparameter, and this is the score. And so you can kind of see visually how, for most of the space, the cross-validation score is higher than the test score. It's interesting. I don't know why this is happening over here, that the cross-validation score is worse than the test score. That could just be luck. But yeah, I wanted you to notice this optimism here, which is what we saw last time, but I think it's nice to see in the plot. And it also shows that cross-validation doesn't necessarily pick the best hyperparameters. Because the data set was small here, you can see this blue curve for cross-validation is super bumpy. And so it's kind of arbitrary, like, is this the best hyperparameter? Is this the best? This bumpiness is not real. It's more because of the small data set, whereas we had this big test set and we can see this smoother curve. So I think this plot is just a nice way to illustrate A, that the cross-validation score can be too optimistic, and B, that when you pick the best hyperparameters based on cross-validation, it might not actually be the best hyperparameters, but it's kind of, well, and we've been having this discussion for a long time on Piazza and in the course of, okay, well, how should I pick my best model, especially if I have a small data set or if I'm doing a lot of hyperparameter optimization? So I actually started reaching out to some people in industry over the last few days, and there's definitely no straight answer, which made me feel better about myself, but may not help you that much. But there is some consensus, I think, that if you're shooting in the dark, taking a simpler model is a little bit safer, in the sense that it might do less crazy stuff. And so I talked about that a bit on Piazza as well. But for the purposes of this course, we're basically going to say maximizing cross-validation score. Well, I wrote this all on Piazza already, but maximizing cross-validation score is kind of a reasonable thing to do, but be vigilant. Look at the different scores on the different folds. Look at the test score. Go into this with your eyes open of all the flaws of just looking at cross-validation score. And you may opt to, for example, take a simpler model that has a similar cross-validation score. And realistically, there might be a whole bunch of other considerations that we're not even talking about in this course when this is deployed, like the cost and drift over time and all these other kinds of things. So long story short, there's not a clear answer, and taking the best cross-validation score is kind of a common thing to do. It's an okay thing to do, but it's good to be a bit more careful and at least know what you're getting yourself into. Okay, so that was that. Got some learning objectives. Why is this code run? Usually like to restart everything. Okay. Okay, so dealing with missing data abridged version. So we're basically going to do the quickest, simplest treatment of this issue. It is something on my mind of something I'd like to improve in future versions of this course. I already did a lot of things to this lecture, so I didn't change this particular part, but you would really want to take a stats course to get the full story on missing data, and we're just going to basically talk about a scikit-learn function for dealing with it, but not really say much about it. So just to set your expectations, this is not the be-all, end-all lecture on missing data. So we have this census data set, the data set of the week that we looked at last time. And I'm just going to drop the education column at the beginning because we saw last time that there's already another column called education num where they had coded them in order for us. So that's fine. I'm going to train test split. I'm going to look at some of the data. And so what I'm going to talk about now is these question marks. So these question marks are presumably where the person just didn't answer that question on the census. This person, 90-year-old, asked for their occupation. They just didn't answer it, well, I guess there's a couple possibilities here that this was an actual category, like not applicable because they're retired, or they just didn't answer the question. But in general, you might have missing data in your various data sets that you're looking at. And usually these pandas functions will tell you about them. So if I call .info on the data set, it's telling me non-null. So how many of these things are actually present? And we have 26,048 rows in our data set, and it's saying not everything is not null for all columns. And the reason for that is because in pandas, there's this NaN, which stands for not a number. That's like the official code for something being missing. But in this data set, they were put in as the question mark string rather than the NaN. In other data sets, it might be coded differently. So what we can do is we can replace the question marks with, this is numpy dot not a number, that's that special symbol. And so we can see we have not a numbers here. And then what we can see here is there's actually not the full 26,000 that are not null. And if you use pandas profiler that we talked about last time, which told you about null values, it would now pick up on these missing values. Whereas with the question mark, Python has no way of knowing question mark is anything other than just another category. Now, you could have just decided to ignore this problem here and said, you know what, question mark is another category, I'm just going to leave it in, and that would be fine. But if you had a question mark in a numeric column, for example, you would need to deal with that because you don't want a string in the middle of your numeric column. And in general, for other data sets, you can easily have missing data that you need to do something about. So yeah, the simplest thing you can do is just throw away that data. So I'm going to make my X and Y here. So pandas has a drop NA method, pandas data frames, that basically says, just drop any row that has an NA value in it, a null value in it. And if you do that, then you go from 26,000 rows to 24,000 rows. So that's kind of the simplest, dirtiest treatment of this issue. Just say, you know what, I don't like this, I'm just going to get rid of it. But we need to think things through a little bit here. I mean, this isn't a very satisfying approach because, well, for a number of reasons. So one is, what if we have a missing value in deployment? So we're actually trying to use this to predict someone's income level given these attributes, and then they have something missing, and then our code just breaks because we didn't build into our pipeline a way of dealing with missing data, and in train, we just threw them all away. That could be a problem. And so there's also an issue that, again, would be discussed more in stats courses of, well, this is kind of dangerous because what if we're systematically dropping a certain type of data and biasing our whole model? So not a super fan of this. You can also drop columns. So axis equals 1 says drop all columns with a null value in it. Here, that doesn't really make sense because you've just thrown away 3 perfectly good columns that had a few missing values in them. But it might make sense if you had a column that was like pretty much null in every single case except one case. Yeah, okay, we don't really need that column. We can just throw it away. Again, for this particular data set, I'm not actually sure if those are missing values or if that's just like a category in the census, but in the general case, we can definitely have missing values, and it's very common. So the other thing you can do that we're going to talk about in this course is imputation, which basically means inventing values for the missing data. So just filling them in somehow, basically. And the way we fill them in depends if it's numeric or categorical columns that have the missing value. So in this data set, those question marks only show up in the categorical features. And so we essentially have a transformer from scikit-learn that that fills them in. So it's called simple imputer. It's the only one we're going to talk about. It's just like the most simple way of handling this. And so this strategy, most frequent, basically says, look at a column find the most, only for categorical columns, look at the most common answer to that question and just fill in the missing ones with that most common answer. And then it's just the same thing as before. You call .transform, you put this in a pipeline. So this is a transformer just like the other transformers we've seen, and use it the same way. You can also use another strategy that just says fill it in with a particular value, so like question mark, and make that its own category. And for numeric features, you can do things like take the average value of that column or something like that. So just filling in the values in a super simple way to deal with missing values. So I've split up our columns into these different types like we did last time. I can fit my imputer. I'm just going to do it on the categorical features because that's the only ones that have missing values here. And I can run this messy code that we don't really need to look into much right now. And I can basically say before we had these nans, these null values, and after we transformed, we had them filled in. In this case, these null values here got filled in with private, which was the most common, the most frequent category in that column. And here, this occupation got filled in with prof specialty because that was the most common. For this particular data set, I would guess it's better to just leave it alone with the question mark. And so it's kind of a domain-specific choice. But I'm illustrating to you the different options of imputation. So this was the other one I mentioned, is you can just say, you know what, every time something's missing, I'm just going to fill it in with a certain value, like question mark. And so if you do this here, in this case, you'll actually get back to the original data set that had question marks and the nulls. Okay, so we can build a pipeline out of this. And I think this is now our first pipeline with 3 steps in it, because up until now, we just had a transformer and then a classifier. But now we have a 3-step pipeline. We have an imputation step. We have a one-hot encoding step. And this is what we talked about last time, encoding categorical variables. And we have a logistic regression classifier. And so if you remember this crazy image from a few classes ago, that had 2 transformers, this is actually now the situation we're in. We have 2 transformers. So there's one transformation, then another one, then the classifier. So I just want to bring this image back for our 3-step pipeline. And so we can run the pipeline, so we can do cross-validate the pipeline. I'm just taking the categorical features for now. We'll deal with the numeric features in a minute. So these categorical features get the imputation done, they get the one-hot encoding done, and then they have a logistic regression, and you can run the whole pipeline. I must not have run this cell up here. You can run the whole pipeline, and it's now doing all those things, and we get the results. So that's all good, but a big thing we need to talk about later today, which we'll do after the break, is, well, this was only the categorical features, but we need to deal with the numeric features, and we need to use all of them for our prediction. And so that's kind of where we're going by the end of today, is we'll bring everything together on this census problem. Okay, so now we're at Q&A. So let me first take a look at Piazza. I don't see anything there, which is a bit ominous for the future of Piazza Live Q&A, but there you have it. I'll just post the link in case anyone wants to use it later today. So let me go into the Zoom here. What is axis equals 0? Okay, that was answered. It refers to the rows rather than the columns. Wouldn't just inventing data bias your data too? Yeah. I'm basically punting that to a stats course and saying, you have to deal with missing data somehow or you're going to get an error. And so here's an easy way of dealing with it and not going into it any more than that. Aren't we violating the golden rule by replacing the missing data? In the most frequent case, you're now looking at all the rows to pick the most frequent, and then you're filling that in. And so you would have that same problem we talked about earlier, except that we're using a pipeline, which, as we talked about, solves that problem because it's separately, every time there's a split in cross-validation, it's separately doing all the steps. So it's separately deciding what is the most frequent and then filling them in and then figuring out what the categories are and then one-hot encoding them and then fitting the logistic regression. And so we're covered by using the pipeline. Okay, I think that more or less covers it, and we have a lot to talk about today, so I'm going to keep going. The next thing we're going to talk about is feature scaling. And so we're going to shift the focus from categorical features to numeric features. All of Tuesday and what we just talked about now. All of Tuesday was about categorical features. Imputation applies to both types of features. And the scaling that we're about to talk about pertains specifically to numeric features. And so let's look at the numeric features. Here they are. We have age, we have this weight thing, which I looked up on the Kaggle page, and you can do that too. We have the education, ordinally encoded, so we're now treating it as numeric, and we have something about their finances and probably how many hours a week they're working. So first thing I can do is I can train a model using only these features. So before I was throwing away the numeric and only using the categorical, now I'm doing the other way around. And the code runs. So I get cross-validation score of around 80%, training score of around 80%. And to compare this with dummy classifier, well, this is a little bit better than dummy classifier, which gets 76%. To remind you, that's because we have 76% in the lower income category and 24% in the higher income category. So this is doing something. Even with only the numeric features, it seems to be doing better. And maybe I should get in the habit of not calling .mean and just get us all in the habit of looking at the individual scores so we can also see that they're pretty close to each other here, and that gives us more confidence. Okay, so we do a little bit better, and we can look at the coefficients of logistic regression, and we can see what they are for the different numeric features. And we can see this coefficient for this final weight feature is pretty tiny. I guess it's 4 times 10 to the minus 6. And so why is this coefficient so small? The reason this coefficient is so small is if you remember what the numbers were, well, these final weight things tended to be pretty big. So on average, apparently 200,000 for this feature. And remember, the way logistic regression makes predictions is it multiplies the coefficient by the actual feature, and then it does that for every feature and adds them all up. So if you're multiplying by huge numbers, then you probably want to multiply it by a small number so that otherwise that feature would just be completely dominating the entire prediction. And that's something that's a little bit worrying, in a sense that, well, we shouldn't really care that much about the units of our features. Like, what if capital gain and loss were measured in thousands of dollars instead of in dollars? We don't want that to mess up our whole machine learning. It shouldn't really matter if the data was collected in dollars or thousands of dollars. It's still the same information, right? And so it should be equally useful for predicting. And so what I'm doing here is I'm simulating that by making a new version, a copy of the data. And I'm dividing by 1,000 here as if these are now expressed in thousands of dollars. And just to make things more, I guess, extreme, I'm also making these numbers even bigger, which again shouldn't really matter. It's just a question of units. But if I do this, so now here's the thing, and this is in thousands of dollars, and this was just multiplied by 1,000 because I felt like it. And I get the cross-validation error. Look at this. This was so bad that the accuracy actually went all the way down to dummy classifier. It's basically saying logistic regression is basically doing absolutely nothing here. It's just doing the same thing as dummy classifier, which doesn't even look at the features. So this should really worry us because I don't want to find out that all my effort in machine learning was messed up because someone measured something in thousands of dollars or millions of dollars. Like that really shouldn't matter. And it has to do with the way logistic regression works under the hood. The fact that these coefficients are getting multiplied by these feature values, and it actually has to do with that C hyperparameter of logistic regression. This effect goes away when C is very large. And someone wrote in the survey last week that I should stop talking about CPSC 340, but I like talking about it just to kind of give you a sense of where this is going. And so I hope you'll forgive that. But in that course, we really go into the math of this and get into the exact details of why this happens and what happens for different values of the C hyperparameter for logistic regression, and kind of demystify this effect. But for here, we're just going to say, with logistic regression, rescaling the features messed everything up and just made it so bad that our accuracy was all the way back down to dummy classifier accuracy. And that worries us. And just as a quick, by the way, decision trees actually don't have this problem because they're only about thresholds. They're just like, is it bigger than that? Is it smaller than that? And so the multiplying doesn't affect them at all because they're not really like directly using the number. So I can just show you that on the original data set and on the modified data set, the decision tree actually gets the exact same score. It's not affected whatsoever. So some machine learning models are affected by this, some aren't. We're not really going to go into which ones are or why in this course. We're just going to solve this problem by rescaling the features as a default good habit that we're always going to do. There's hardly any harm in doing it, so we'll just always do it, and then we don't need to think too hard about, are we using a classifier that's affected by this? We'll just solve the problem. And so we'll get to that in a second, and the scikit-learn for this in a second, but just to tell you where we're going, we're basically going to rescale the features so they're all kind of smushed into the same range before we start. And then that's going to solve this problem because it won't matter what units you started in. So let me get to the Q&A now. Still don't see anything on Piazza. Let me look at the Zoom chat. Just give me a minute. Okay, I'm going to skip the stuff about imputation. What is a good threshold for how close the scores are? Test and train. Yeah, there's no answer to that really. It's all kind of an art. Like, am I overfitting if the train and test are 3% apart, 10% apart? I don't have a general answer for that, and I don't want to go into that right now in the interest of time. Should we normalize the features? Yes, that's exactly what we're about to do, so hang on for that. I'm subtly plugging 340 so we end up taking it with me. Well, I mean, sure. It would be great to have all of you there. There's a giant wait list, so I'm not really trying to recruit more people. I just thought it might be useful for you to know where this would lead if you were interested. And yeah, okay, let's keep going. Okay, I'm going to keep going. So there's two main approaches I'm going to introduce to this rescaling thing. One is called normalization, and that basically smushes the column so that all the numbers in that column are between 0 and 1. So the smallest value of capital gain that you had gets mapped to 0. The biggest one that you had gets mapped to 1. And then everything gets kind of linearly scaled in between 0 and 1, depending on where it falls between the smallest and the middle. So here I have some NumPy code, but it's not really that important. And the other one is standardization, which shifts everything so that the average value is 0, and then rescales everything so that the standard deviation is 1, which is the same thing as saying that the variance is 1. And so I'm not going to go in too much. Okay, in a later lecture, I'll talk about the pros and cons of these approaches, but right now I'm just going to say either one more or less gets the job done for today, and I'm not going to go into a comparison quite yet. So here I import these from scikit-learn. And again, these are more transformers. We're now seeing lots and lots of transformers. So it's all the same thing. I can fit one of these standard scalars on the numeric features, and I can transform it. And okay, this output is not very readable, so I need to make it into a data frame. I can transform it, and what you can see here is we use standard scalar, which was this one, does standardization. And so what it did here is it set the average value to each column to 0 and set the standard deviation to 1. So you can see you don't have values like a million here, because that would mean a million standard deviations above the mean, which is not going to happen. So this is saying 0.7 standard deviations above the mean, 1.3 standard deviations below the mean. That's how you can interpret these numbers. And so, yeah, coming back to the golden rule thing again, this is a transformation where each row is affected by all the rows, because it needs to look at the whole column, compute the mean, look at the whole column, compute the standard deviation, has to subtract the mean for everything and divide by the standard deviation for everything. And so we do want to use pipelines here with our cross-validation. Okay. So I'm just doing it the same as for test. Up here I did it for train, down here I'm doing it for test. And another thing we can do here is after we've scaled it, we can actually compute the mean and the standard deviation. And so what we can see here, if we take the mean of every feature, is that they're extremely close to 0. So that mean for age is 3 times 10 to the minus 16. With numerical computing, you don't always get exactly 0. We talk about that in some other courses like CPSC 302 or 303, but we can just say, hey, this is basically 0. This is extremely small, 10 to the minus 16. So it did what it was supposed to do. When we looked at the scaled data frame, which was this one, and we looked at the average of each column, the average of each column was 0 as it was supposed to be, and the standard deviation of each column was basically 1 as it was supposed to be. And note that if we do the same thing for the test data, the mean isn't 0. So this is 0.02 or 0.02 again. And the standard deviation isn't exactly 1. It's 1.02. And that's fine. So going back to our count vectorizer discussion from a couple of weeks ago, we do not want to fit transform on the test data. It's the same thing. We want to fit on the training data, compute the means, compute the variances, and then subtract off those means and divide by the standard deviations that came from the training set. And so this test thing, each value had the mean from the training data subtracted off. And since the test and train may have had slightly different means, we don't get exactly 0, but that's actually what we want, because we want to perform the same transformation on the training data and the test data for all the reasons we talked about back then with count vectorizer. So I just want to point out, if you ever see something like this and you're like, hey, I scaled, but now the mean isn't 0, don't freak out if you're looking at your test data, because that's normal. The mean should become 0 in the training data, and now you're just performing that same operation on the test data, because that's what you want. You want to have pre-processed them the same way. And so that's all fine, because your classifier is expecting something pre-processed in that way. So I think that's a common point of confusion I wanted to point out. I don't actually have a Q&A block here, but I think this would be a good time, because there's quite a lot going on here. So let me see if there's any questions. Just one question. What is the drawback in normalizing the whole data set before split? Doesn't sound like a golden rule violation. So it is a golden rule violation if you do that before the splitting, because you'll compute the average of a column on all the data, including what will later become the training data and what will later become the test data. And so then the training data will be transformed. There will be an average subtracted from it where you use the test data to compute that average. So it's again subtle, like it was with count vectorizer, but you are leaking information from the test data into the training data, maybe not in a earth-shattering way, but we shouldn't do that kind of thing. The test data should be unseen. And so we don't want to transform the training data using a mean and standard deviation that was computed from the test data as well. Okay, so we can rerun our experiments now. So here's the original data set that I didn't mess with. And so this is the exact same 80% that we saw 5-10 minutes ago. Nothing different here. And now I'm going to add scaling. So I'm going to make a pipeline with standard scalar followed by logistic regression, still on the original data set. And so what we see here is, remember, this was not the data set I tempered with. This was just the original as-is data set, but we already get an improvement here. And the reason was the scaling was already kind of out of whack even before I messed with it. That final weight thing was up to like 1 million, and the age was up to 100. And what we kind of want is for each column to be on an equal playing field. And so final weight having those giant values was already kind of dominating more than it should have. And by putting in standard scalar first, we actually got better train and test score, which is awesome. And part of what I'm trying to say here is this is basically often a good idea and almost never a bad idea. And so you can just make it a habit to always do this when you have numeric features. But now let's go back to the data that I messed with. So this is this mod thing. This is the data that I messed with by making the capital gain and loss even smaller and the final weight even bigger. So this is the experiment that we saw earlier, that it was junk. We got the dummy classifier score. But if we take the data that I messed with, but we scale first, then it unmesses up the messing up that I did, because I multiplied something by 1,000, but hey, we're dividing out the standard deviation anyways. We're kind of dividing out the scale of the feature. And so if I divide it by 1,000, the standard deviation got smaller by 1,000. If I multiply by 1,000, the standard deviation got bigger by 1,000. So if you're scaling, it makes no difference if your thing is in dollars or thousands of dollars. It makes no difference if your age is in years or months or days or minutes, because that all gets divided back out by the scaling. And you'll see this 81.4 and 81.5 is literally to every decimal exactly the same number as here, because it's the same thing. I did a multiplication by 1,000, but then it got divided back out by that same 1,000 over here. So that's good. Any questions about this? You never know if no questions is people are following or they're so lost that they don't even have questions. But let's hope that it's the former. Oh, here we go. Thank you. As long as we have numeric data, should we normalize? Yeah, that's basically what I'm saying. Yeah, I'm basically saying part of the point of this course is to give you reasonable defaults of here's just like things I should do almost all the time. And I hope you'll be better off having taken this course and having those kind of defaults in your mind. And I think this is an example of a reasonable default. If you just do this every time you have numeric features, 1 in 100 cases, it might be slightly bad for some nuanced reasons, but I think it is a good thing to do. So yes, I'm considering it, putting this on our list of best practices for you all to do, unless you have some strong reason not to. For some classifiers, it'll just make no difference, but I don't think it's going to harm either. But for some classifiers, like logistic regression or other models, it'll be a very good thing to do. Okay, so I mentioned standardization and normalization. The one I just showed you was standardization. This one is normalization. It's basically the same thing, except it puts the range into 0, 1. So first of all, we can see we get kind of the same accuracy, 81%, if we do this one instead of that one. And we can also just peek into the details and see, I call fit on train, I call transform on train, I call transform on test. And I can see, I'm calling .min, so get me the minimum value. So you can see the minimum for every column is now 0. The maximum for every column is now 1. Actually, it might have been nicer to just go. Oh, I see. It's not actually a data frame. I just said it was a data frame. This is a lie. Okay. And then for test, again, for test, it's not exactly 0 and 1 because I took the minimum from the training set. I took the maximum from the training set. That got stored inside of fit. So actually, this transformer object, stores the min and the max. So basically all it's really doing when you're calling fit is it's looking at every column and just saying, what is the minimum of that column and storing it? What is the maximum of that column and storing it? That's all it's really doing. And then it's when you call transform, it's just shifting everything because it has that information. So same with standard scalar. You can actually look at the transformer object and look inside it, and you will see that it has stored for each column the mean and standard deviation. Okay, the last thing I want to say on this is that we're talking about pre-processing the features, the x's, the inputs. In a couple of weeks, we're going to talk about regression, which is where the y value is numeric. And when we get there, we will talk a little bit about possible pre-processing options on numeric target values. But since we're still just doing classification right now, where the y values are categories, we don't need to worry about this for now. Okay, let's see, other questions? I'm just looking at the chat. Okay, yeah, I think this is stuff we talked about before. Okay, let's call the break. So let's stop here and come back at 11:44 in 5 minutes. Okay. Fasten your seatbelts. It is time to talk about ColumnTransformer, which is going to be pretty great. So here's the mess we're in. Let me tell you about the mess we're in right now. We have a way, what we've talked about to deal with categorical features. So in this case, we decided we're going to use imputation. We decided we're going to use one-hot encoding. We talked about this last time, and we're just sticking with logistic regression for now. So this is our deal with categorical features. And likewise, we have a pipeline for numeric features. In this case, I just happened to know there was no missing values, so I skipped to the imputation step. We have our scaling and our logistic regression. However, these two pipelines are kind of useless because they have two different logistic regressions in them, but we want one logistic regression that takes in all the encoded categorical features, takes all the scaled numeric features, and makes one giant data frame out of that, and then learns does fit once on everything. We can't split this problem up because it needs to see all the data together to deal with this. And when learning the coefficients, it needs to see everything at the same time. And so we can do that. Here's the very awkward non-pipeline approach, which I'm not advocating for. So I'm just setting up here our 3 transformers. I'm setting up our classifier. I'm now going to process the categorical variables. So I'm just going to subset the categorical features. I'm going to fit transform the imputer. I'm going to fit transform the one-hot encoding. And then I'm just going to display it in a data frame just for the purpose of looking at it. And here's what we have. This is the result of our pre-processing for categorical variables, and it's basically just the one-hot encoding we saw last time. So we have all these zeros and ones, like we talked about last time. And now we can do the same thing for the numeric features. We can grab the numeric features, we can do the scaling, fit transform, and then we can look at it. And here they are. This is what we saw before. And now we can smush them together using a pandas function. And great, now we've smushed them together. Now we have that giant data frame I talked about that has all the scaled numeric features over here, has all the encoded categorical features over here. This is the data frame we want to pass into logistic regression, and we can do that. We can pass it into logistic regression, and it works. There's no errors, but this is just a disaster. I mean, I had so many lines of code, and furthermore, there's no pipeline here, so I have these golden rule issues if I want to do cross-validation, and furthermore, I have to take all those lines of code I just showed you and do them again on the test set. So yeah, I don't want to do this. This is just a horrible mess. And so we're going to have this new thing called ColumnTransformer that's going to come in and save the day. And so what ColumnTransformer, it's kind of like Pipeline, it's kind of glue. It's kind of scikit-learn glue. It's, I guess it's technically a transformer maybe, but it's more of like a meta transformer. Again, like Pipeline is kind of this meta thing. And so I'm going to import it. And here's kind of the high level view of what's going to happen. We have different types of features, which are columns. So maybe we have a bunch of numeric features, we have a bunch of categorical features, maybe we have some other type of features. In this case, we don't, but you could imagine maybe you did. And so what ColumnTransformer is going to do is it's going to allow us to specify what do you want to do to each of these types of features. Well, we want to scale the numeric features, we want to one-hot encode the categorical features, and in this example, in this picture, we've decided that for the other columns, we don't want to do anything to them at all. And so that's what pass through means, just pass them through without changing them. And here's our transform data over here, which is this. This is what we're trying to get to, right? Now we have these new numeric columns that have been scaled and the new categorical columns. And the person who made this picture did a great job because you can see they were clever. And then the width of this yellow thing is the same as the width of this blue thing. It's basically saying we haven't changed the number of numeric columns, but we've actually gotten ourselves more categorical columns because remember, one-hot encoding makes more columns. So great picture taken from this other course. And this is very nice, and it's going to give us a lot of benefits like Pipeline did to just reduce the clutter and mess in our world and prevent us from accidentally forgetting things, from accidentally messing things up, accidentally violating the golden rule, etc., etc. So here's the basic syntax for ColumnTransformer. Like Pipeline, you pass in a list of tuples. So that's what we were doing with Pipeline. The square bracket says we're making a Python list, and these parentheses say we're making tuples. That's what we've been doing all this time with Pipeline. And like Pipeline, the first thing, the tuple, is what you're going to call it. The second thing is the object, be it a transformer or a classifier. And now with ColumnTransformer, there's a third entry in each tuple, which says which columns is this going to be applied to. And so here we're saying we want to apply scaling to our numeric features. And remember, this thing is a Python list with the names of all the numeric features. And here's what I want to do to all the categorical features. I want to one-hot encode them. We'll ignore the imputation for a second. This sparse equals false thing, we can just ignore that for now. We will talk more about that in a few weeks. Okay, so yeah, similar syntax to Pipeline, but a little different. I can run this. Now I have this ColumnTransformer object. Its type is a ColumnTransformer. And it has the same methods like a transformer. It has fit, it has transform, it has the shorthand fit _ transform. And so here's what I can do. Again, I'm skipping the imputation, so I'm taking the already imputed data set just for a moment. So I can call fit transform, and it just does all the things we just talked about. It scales the numeric features, it one-hot encodes those, and then it smushes it back together for you. And so I actually rather put this on its own cell just to emphasize it. This does all of that magic for us. And so it already works. I mean, this is already a bunch of numbers. But again, all these scikit-learn functions, they keep outputting NumPy arrays, which is why they're printing out like this. And so it's just hard to read these NumPy arrays. So that's why you keep seeing me do this over and over again, put things into a pandas data frame just so it prints out nicely. So first I have to figure out what the new columns are. And this is kind of messy. So the numeric features stay the same. So the column names stay the same. But for one-hot encoding, I now have a bunch of columns. And this messy code is basically grabbing the one-hot encoder from the preprocessor and saying, tell me the names of the columns you made. And we saw a bit of that in a bit less messy form on Tuesday. Long story short, if I have the name of the columns, I can actually look at it in a more appealing way as a pandas data frame. And hey, we got the thing with so much less mess. This is really great. So ColumnTransformer did the things to the different sets of columns. It did the smushing. Now I can also call this on test. All I have to do is go preprocessor.transform x test. And bam, I don't need to have my 10 lines of code copied and pasted for the test set. So this is pretty great. It's very handy. And when we call fit on the column transformer, what is it doing? So in fact, I kind of feel like this was a bit, I think for the first time, it would be a bit better to just really do it a bit more slowly. So first, when we call fit, it's actually fitting all the transformers in the column transformer. In this case, there's only two. So it's fitting the scalar, meaning it's learning the means and standard deviations. On the numeric features, it's fitting the one-hot encoder, which means it's checking what categories there are. So like pipeline, when you call fit on pipeline, it calls fit on all its constituents. It's the same thing here. And when we call transform, it's now calling the transform of standard scalar on the numeric features, calling the transform of one-hot encoder, making all those columns on the categorical features. Right, so it's very handy. And yes, important warning here. So by default, let me go up to this picture. Actually, so here I specified numeric features and categorical features. And it just so happened that all the columns are accounted for in these two lists because I don't have anything else. If I look at all these, that's all the columns. But if I had more columns that were not accounted for in here, those would actually just get thrown away by default. And often we don't want that. We actually want, what we were trying to say is, no, just leave those columns alone. Don't column transform them, but don't delete them either. Hey, I wanted those columns. And so that's why these pass-through columns, you actually have to tell it, remainder equals pass through to say, hey, all the columns that were not accounted for, can you please not throw them away, just pass them through. So that's what this warning is, and that's what this is saying. Okay, let me pause for questions. I guess there are there any questions? Please do use Piazza, since we're giving it a test run right now. Please do use the live Q&A if you have questions. I don't see any questions there right now. I don't see any in the Zoom. Let me just wait 30 seconds to see if anything appears. What about the imputer? Yeah, okay, well, we're gonna get to the imputer right now. So let's move on. Okay, so we wanna put everything in the pipeline now. Because remember this, what we just talked about, it only did the transforming. It only did the scaling or one-hot encoding, but it didn't do the logistic regression part. We still want a pipeline. And furthermore, there's the imputer, as someone correctly stated. So yeah, what I might want is I might wanna run the imputer on, so I'm gonna make a pipeline. This is where it's getting kind of wild. Well, depending on your definition of wild, but I have a pipeline with a column transformer inside the pipeline as one of the steps. So my pipeline says impute on everything, which is fine in this particular case because there's only missing values in the categorical features. This is not generally that great because most let's just move on. So do the imputation on everything. Then do this column transformer, which remember, it like goes out into the two types of columns, does their separate things and brings it back together. on the output of simple imputer, and then on the output of that, run the logistic regression. And so this looked reasonable to me when I wrote the code. So this used to say approach number 1, and then I had to change it to attempt number 1 when I realized it didn't work. So let's run it. So I call pipeline.fit, and I get an error. And we can see part of the error message, NumPy array has no attribute columns. Specifying the columns using strings is only supported for pandas data frames. So as I mentioned a couple minutes ago, we're doing this dance between NumPy arrays and pandas data frames. Pandas data frames are like a wrapper on top of NumPy arrays. Under the hood, they are basically NumPy arrays, but they're a lot nicer for us to look at because we can actually see the names of the columns, and they have all these nice features. So I keep bringing everything back to pandas for our own sanity as humans here. But the problem is that any scikit-learn transformer, when you call transform, it outputs a NumPy array. At least I'm not aware of any way to prevent that from happening. So this was the first step in our pipeline, and if I just call this, it outputs a NumPy array. We can look at the type, for example. It outputs a NumPy array. And so the thing is that, yeah, we can put that into a data frame ourselves and look at it like this, and that's all well and good. But the problem is that ColumnTransformer, we refer to the columns by name instead of by index, which I personally like. I think it makes way more sense to say, here's the names of the columns rather than like column 7, column 9, column 13. I feel like that's more error prone. And so I like referring to the columns by names, and now I'm going to scroll up, sorry. I'm going to copy and paste. I try to avoid scrolling because I know it's a little whack to watch that. So here's the thing. Our pipeline is taking this first step, which is outputting a NumPy array, which would have been fine before because logistic regression can take in that NumPy array. But we're outputting a NumPy array and then passing it to this column transformer, which is trying to refer to names of columns. That is where the error is coming from. And so that's why it's all getting messed up. It's saying, hey, you tried to reference names, but you're giving me a NumPy array. So it's kind of a syntax subtlety. I don't want us to get too hung up on it. But I'll show you a different way of coding it that will not have that problem. And maybe there's other ways too to get around this that I'm not aware of, and you can let me know if you find some. But well, I can think of some ways. But anyways, any questions about this error? Why not have remainder equals pass through always? Yeah, I think that's fine. I think you can just do that all the time. Maybe they'll even change the default one day. So ColumnTransformer is just a pipeline for preprocessors. Well, no. So I don't know if you all have taken physics, but in like circuits, there's like series and parallel. And so pipeline is like the resistors in series from physics. It's like do this and then do that and then do that. And ColumnTransformer is like the resistors in parallel from physics. It's like do all these things together. Some of the, it's not a perfect analogy, but do this thing on these columns, do this thing on these columns, do this thing on these columns, and then bring it back together. So it's not sequential. It's not doing one thing, getting the output of it, and then doing something to the output. That's what pipeline does. ColumnTransformer is just doing one step, but it's doing different things to different columns of the data frame. Didn't we want to only impute the numeric data? In general, we may need to impute all the data because we may have missing values in both types of columns, but in this case, we just happen to only have those missing values in the categoricals. Okay, so here's what's going to actually work, and someone called this out earlier in the chat, so nicely done. So what I'm going to do is I'm going to make a separate pipeline for each feature type for just the preprocessing. So let's make a pipeline for the categoricals, just the preprocessing. I'm going to have an imputer. I'm going to do this imputation, then I'm going to do the one-hot encoding. That's the preprocessing. for the categoricals. For the numericals, we don't actually need a pipeline because there's only one step. It's just standard scalar. But in general, we might have needed a pipeline for the numericals too, because we'd need to use simple imputer with a different strategy, like taking the median of all the numbers is a reasonable way to fill in missing data for numeric variables. So we might have a pipeline for numeric that says impute by taking the median of the column for the missing value and then scale after that. And that would be an example. Here we just didn't need that because we only had one step, which was scaling. And then we put this together in a column transformer. And so the column transformer says for categorical features, do this entire sequence of steps for categorical features. And for numeric features, do this entire sequence of steps, which could generally be a different pipeline object. In this case, it's just one step, so we didn't need to do that. Okay, and now here's where it's going to get, well, not messy. Here's the next thing we're going to do. We're going to make a pipeline that has all the pre-processing and then the classifier. And so, yeah, this thing is a little, someone said in the chat earlier, nested pipelines, and that's kind of what's going on here. So the last thing you're going to do is logistic regression. Before that, you're going to do all your pre-processing. And what is all your pre-processing? Well, it's split up into, I feel like there's a picture is just drawing itself in my mind here. I should really get you a picture after class. All the pre-processing is, well, I'm going to do something different for categoricals and I'm going to do something different for numeric. And what am I going to do? Well, the categorical part is going to be a sequence of steps. And the numeric part could be potentially another sequence of steps. And so you have a pipeline, and inside it you have a column transformer, and inside of that you have potentially more pipelines, which is kind of heavy syntax-wise, but also, to me at least, feels kind of organized. And importantly, is not going to throw that error because there is no step here before the column transformer. So since the column transformer is the first step, we don't have that numpy array issue. We pass into pandas data frame and it immediately goes into the column transformer. And so it can understand based on the column names, okay, for these column names, do this whole pipeline. For these column names, do that whole pipeline. And then it gets around this error and will hopefully not throw an error this time. Okay, yeah, so just so many things happened when I called pipeline.fit. I feel like this could be an exam question or something. Like this called the fit of this, which called the fit of this, which called the fit of this, and then the transform of this and the fit of that. So I did have on the previous homework, which you already turned in, like a little bit of unpacking of the steps where you had to do it manually. But here there's even more steps. Because we didn't deal with this whole categorical variable, numeric variable thing. We just had the count vectorizer last time. And then I can call predict here. And again, a lot of steps are happening here when I call predict. It's transforming all the things and then calling predict on logistic regression. Yeah, so I think this is cool. I don't know if you agree, but it's just all the things are in this final pipeline, and you can call predict on the test data, and it's just harder to mess up, I think, when you do it this way, because the fear is that you accidentally do something different on your test or deployment data than you did on train. You accidentally use slightly different hyperparameters on your scaling or a different type of scalar, or you skip a step or a different type of encoding. Whereas here, since it's on this pipe object, and when I call pipe.predict on train or on test, I know it's just doing that exact same series of transformations in both cases. And that's reassuring for me in terms of not messing something up. And furthermore, I can call cross-validate. And it all works, and I don't have to, the golden rule thing is taken care of, and I can pass this into randomized search CV, and that's all good. So yeah, That's all very nice. Oh, and just reminding you that I'm passing in the raw data here, just like we did last time, because the pipeline is doing all the transformations, and so I'm passing in the original raw data with the null values. Okay. Questions? Yeah. So someone is saying they're hoping for a more elegant solution. Is there really no better way? See, I think this is pretty good personally, because you start by saying what all your steps are, and then it's all ready to go, and then you just do it. In my personal experience, what's extremely error prone is the other thing I showed you. If I can just scroll up for a minute. Sorry, but this is the thing that I find is extremely error prone, is when you take your actual data and you yourself keep transforming it one step after another. I find that part is the part that's actually extremely error prone. You're so likely to mess something up. And then you have to copy and paste all this for test, which is, first of all, just like not a good software engineering practice to be copy and pasting code. I guess you could like rep it in a function. And then you have to be so careful that you're fitting on the train and not on the test. And yeah, I mean, we are actually doing something very complicated here. So maybe we can't ask for like a one line of code thing, because we're really doing a lot here. I'm going to scroll down. Scroll down more, sorry. Where was I? Right. So I don't know. I find this pretty nice. Like, here's all the steps I need to do to these type of features. Here's all the steps. Oh, here's all the steps I need to do to those types of features. Now I say, do this to these, do this to these, and then do all that, and then this. So yeah, again, I find this less error prone, and not messing up the golden rule and all those other kinds of things, especially in terms of making sure I do the same thing to train and test. Yeah, so the question is, to clarify, ColumnTransformer, make sure our categorical and numerical data preprocessing happens in sort of one step. Yeah, it basically automates the idea of doing different things to different columns and then gluing the outputs back together afterwards. So yeah, that's what ColumnTransformer automates for us. Yeah, I mean, in reality, it's not literally happening at the same time, like on the level of my laptop, but we can conceptualize it as happening at the same time. Okay, it looks like we're on schedule, which is excellent. So the next thing is revisiting hyperparameter search. So we talked a few classes ago about grid search CV and randomized search CV, and we talked about this syntax. We had a pipeline last time, and we wanted to say, what is the C of the logistic regression? So we did the name of it. Last time it was LR, it doesn't matter, classifier, underscore, underscore, name of the hyperparameter. And that's still the same thing here. But let's say we wanted to optimize over the strategy of the imputer. I don't think it's the most realistic thing that we would really care that much about optimizing. But let's say we wanted to choose the imputer strategy. Should it be constant or should it be most frequent? So how do we get to the imputer? Well, what is the imputer? We're trying to get at the strategy of the imputer of the categorical part of the preprocessing. And the syntax for that is right here. So this is kind of crazy and may take a while to digest, but we basically, again, I feel like I should have drawn a picture here, and maybe I will after class, but just to visualize in our mind, we start with the pipeline. The pipeline has two parts to it, classifier and preprocessing. So we want to go inside of the preprocessing. What is that? It's a column transformer. It has two parts, categorical and numerical. We want to go inside the categorical part. What is in there? Well, that's another pipeline that has two parts, impute and one hot encode. Well, we want to go inside the impute part. And then that's a simple imputer scikit-learn object. And what's the name of the hyperparameter? It's called strategy. And here's the two values of that hyperparameter we want to try out. So Just wanted to expose you to this syntax, and it's not the most beautiful thing, but it's the way of kind of indexing indexing into pipeception, exactly, indexing deep into the pipeline. So just a note here that these names come from these strings here. This string here, it's not the Python variable name that we're referencing. That can be anything. It's the name we gave here. It's the name we gave here. It's the name we gave here. Those are the things that we're looking at. Yeah, it's not the most beautiful syntax. But now I can call grid search CV. I can pass in the pipe. I can pass in this dictionary of hyperparameters. And it should just work. And yeah, by this point, like the thing that is happening right now as we are waiting here, it is complicated. Like it is doing a lot of things right now. It's doing it's trying different hyperparameters for a given hyperparameter. It's doing 5-fold cross validation for each fold. It's fitting on the train part, which involves a bunch of fitting and transforming and gluing together and da 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 da, and then getting the score. And yeah, it's just it's a lot. It's a lot that's happening under the hood here. Okay, so it says it's done. We can look at the results. Again, I just keep making things data frames for the purpose of printing out, and we can see it really explored the different values of C that we asked it to explore, and it explored the 2 different values of imputation. And here, this whole hyperparameter optimization wasn't very interesting or inspiring. I mean, none of these are really overfitting too badly. As you can see, the train and test score are pretty similar, and it's going from 85.1 to 84.8. So my takeaway from this is that changing these hyperparameters is not having a super big effect here. And so I might not care all that much which ones I'm choosing. And then we can run on the test set and do all the things that we are used to doing. I'm going to change my terminology here. I think. I'm kind of using optimization bias synonymously with overfitting on the validation set, but I think I'm going to move towards this terminology. I think that's more standard. Okay, yeah, so here we have a pretty big data set, and that's probably a reason why this was less of an issue compared to what we talked about last class, where we had 500 training examples. So nothing really new here except just the lots of underscores syntax that I wanted to show you. Let me grab one of these, put it here. I'm going to check. Oh, there's a PSC question. Awesome. Transformers preprocessors. What sort of things can be used in the transformation preprocessor sections of the pipeline? Could you use some sort of function to manually transform the data and use that function in your pipeline? Yeah, awesome question. So yes, you can. I think there's a transformer in scikit-learn called function transformer, where you just give it any Python function you want, and it makes a scikit-learn transformer out of that. So I have used that before. And so I guess that could have even technically solved the problem we had before. I guess you could have done that to turn the thing from a NumPy array into a pandas data frame if you really wanted to, and then done attempt number 1, which I showed you. So yes, you can make your own transformers if you want. Okay, I see a few other questions here. When optimizing, do people usually try all combinations? Yeah, not really. So as I was saying a couple of classes ago, I think randomized search is generally preferred by me, and I know I have gone against that by using grid search a few times in class. I mean, here I really want grid search made more sense because there's only 10 possibilities. But in general, I mean, all combinations is also kind of a made-up concept because C is a continuous number. I just picked 5 possible values, but really C is just a number, and so like random search through the continuous space might make more sense. And also, yeah, if you have like 5 hyperparameters with 5 values, each grid search is just not going to happen. You're not going to want to do 5 to the power of 5 different runs. It'll typically be too slow. do we need to optimize these two hyperparameters simultaneously? Why not find the best imputation strategy first? Yeah, so generally speaking, the hyperparameters will depend on each other. And zoom. I added, so I posted on Piazza, and then I added after class, so I can show it to you now. Sorry, I know this is so much scrolling. Yeah, so I showed you this picture, and then I added this picture, which I also posted on Piazza, which says if you fix one hyperparameter and only search the other, that's like a line on this grid, and then you fix that one and only search the other one, you don't actually end up trying all possibilities. And you're right, if they don't depend on each other, then you could do them one at a time, but often they do depend on each other. This example I've been showing you is kind of a contrived case, because I don't think this imputation hyperparameter, I mean, these are not life-changing hyperparameters, but we're going to get to cases later where you have a bunch of hyperparameters and they really do, since they kind of control the same thing, you do need to jointly optimize them. So I definitely recommend that in general. Optimization bias and overfitting on the validation set. Yeah, so they're the same thing. I'm just going to move towards this terminology, but I'm using them interchangeably. Okay, 2 minutes left for the summary, as requested in the survey. So what did we talk about today? We talked about imputation for missing values in extremely low amount of detail, and there's different strategies for categorical variables. You could do something like the most common category, or just make a special category for missing values. For numeric features, you could do something like the median value, which is basically like, we're just going to stick in a typical value for this numerical feature. We talked about scaling, and we basically said is generally a good idea. And I'll just use standard scalar most of the time for now, but there's an upcoming lecture on outliers where we'll talk a little bit more about the implications of this choice, especially in the context of outliers. We talked about ColumnTransformer, which is a really useful piece of glue when you want to do different pre-processing operations to different types of features, and kind of the series parallel idea that pipelines are doing things in series, and we can think of ColumnTransformer as like doing things in parallel. And then we talked about this double underscore syntax to reference these hyperparameters that are kind of embedded deep in the pipeline and the ColumnTransformer. So just one last question. Should we generally choose random search over grid search? Again, a lot of what I'm trying to do here is just give you defaults. And I think random search is a good default when you're tackling a new machine learning problem. Unless there's just such a small value, possible number of values, you're like, well, I can easily try all of them. But I think randomized search CV is a reasonable default. That's all for today. I'll try to get you the homework as soon as I can, and I will see you all next Tuesday.